Hi, in this video we're going to be talking about our different types of functions and what that really means. So what we do when we're doing any sort of science is typically we collect a bunch of data and then we want to look at it. So here's just a random set of data that I've collected and now I want to analyze it. But well, really the first thing that I need to do is figure out if I want to make predictions on this data, what kind of function should I use that models this the best? Well, that's really the reason that every student is required to study mathematics and algebra if they expect to get a college degree. It's because we use those tools of mathematics and algebra to help us predict the future. We take the data and then we create mathematical models that are going to match that data. And then we can use our model or use our function and plug in new values and see what's likely to happen. And that's how we used math and algebra to really create the modern world around us by being able to predict what's going to happen next. But before we can get to those steps, the first step is just going to be to identify which type of model or which type of function it is that we should be using. So let's take a look at the functions we've covered so far in algebra and their key features so that you have a better idea of which function we should use to match to the data in those given scenarios. So the first function we looked at was linear functions. And these are typically the most straightforward of our functions. A linear function is, well, a line. And its key features that we have a constant rate of change. Anything that happens at a constant rate, well, that's something we're going to model with a linear function. Next is our quadratic functions. So quadratic functions, the shape is what's called the parabola. That means that the graph is going to go up and then come back down, or it might go down and come back up. Either way, it makes either kind of a U shape or an upside down U shape with the graph. Then there's our rational functions. So if you remember, rational is just another word for fraction. So anytime we have a rational graph or a rational function, well, if there's a fraction, there's going to be somewhere that denominator is going to be 0. And where that denominator is 0, we get an asymptote. And an asymptote is just a fancy word for a gap in our function. And so you see, again, we clearly have two different parts of this green line, and they are separated by an asymptote. Neither of them reach that middle line, and that's how we know that we're dealing with a rational function with that gap. We also have radical functions, or specifically our square root functions. And the key feature about a square root function is that it's not going to be defined on the entire graph. Essentially, we're going to have a distinct starting point. And again, if I look in the middle of this graph, here's my distinct starting point, and it only continues in that one direction. And it keeps continuing, and it will continue all the way off, well, for infinity. But it has that definitive starting point. And the last function is our exponential functions. These functions will always be increasing or sometimes always be decreasing, but it'll be always above that x-axis. So again, you have your x-axis as that horizontal axis down there, and the function's always going to be on top of that. Although you can see as you get really, really close to the end, it almost looks like it merges together. And it is going to be defined for every value of x. So it is going to be defined across that entire x-axis from left to right. And its key feature is going to be its rapid growth in one direction. Or sometimes, again, rapid decay. Either the exponential growth, which, yeah, that's why that term has entered, common language when things grow really quickly. We have exponential growth, or even sometimes what's called exponential decay. So now that we looked at the key features, again, your job is going to be to look at a graph and tell me what type of function it is. So, what type of function is this graph? Hopefully you guessed quadratic, because we do have that down and back up. Again, it's going in two directions. We have it going down, then there's a point down here where it levels off, and then it goes back up in the other direction, and we have a quadratic graph. What about this one? Now, if you need to pause the video and really think about it. Make sure you actually are making a guess before, well, I tell you what the answer is. And I'll tell you right now that the answer is, it's a radical. And the reason I know that is that I do have, again, a definitive starting point down here, and then it goes in just that one direction for infinity. Next, what type of function is this? Again, take your time, but this one is going to be, well, linear. Anytime you have a line, anytime you have a straight line, which is a bit redundant because every line is straight, but anytime you have a straight line, that's got to be a linear function. Now, what about this? What type of function is being shown with this particular graph? Again, take some time and think about it. And hopefully you have your answer. And hopefully it's the correct answer, which is exponential. This is an exponential graph. This one is a little bit different than the example I showed during kind of the notes portion, because this one is actually showing us exponential decay. We see it's really tall, and then it's getting, well, very small very quickly. But it's always above my x-axis, even if it looks like it's kind of touching over there. And it is defined for that entire x-axis in both directions. Last up, what type of function is this one? And take a few seconds, think about it. I'll tell you that the answer is, this one is a rational function. And again, we know it's a rational function because the graph is separated into multiple pieces. Now again, the one in the notes only was separated into 2 pieces. This one has 3 separate pieces. But again, we can kind of see here that there's definitely a line that forms an asymptote here and a line that forms an asymptote there that separates the function, that gives us that gap. So that is the quick and easy way to identify functions based on their graphs, which is then used later for, well, modeling. But we need to be able to do that first step as a human being before we can tell, well, computers how to hopefully interpret our data. So good luck studying. If you have any questions, please don't hesitate to ask. And goodbye.